Okay, so let's work this tightrope walker example, and hopefully you're looking at the picture that goes with that example. And so in that picture you have the tightrope walker standing on the center of the tightrope, and it's bent the tightrope to 5 degrees from the horizontal. And so let's just go straight to drawing a free body diagram for that situation. And we're going to consider, to calculate the tension of the rope, we're going to consider the little part of the rope right where the guy's foot is touching the rope. Okay? So that little section of rope then is being pushed downward by the weight of the guy's foot with his weight, which is mg. Okay? Now that little point of the rope is being pulled to the right by the tension of the rope that we're going to call TR. So TR goes that way, and it makes a 5-degree angle with the horizontal there. Now that little part of the rope is being pulled to the left by the tension of the rope that we're going to call TL. And that's at a 5-degree angle. Okay, so there's basically our free body diagram there for that little part of the rope. Now, we know that this little part of the rope is stationary. So acceleration equals 0. This is an equilibrium problem then. So if acceleration equals 0 and we use Newton's second law, the net force, which is mass times acceleration, is 0. So what that means is the net force, the total force, the sum of all these force vectors adds up to 0. They're all canceling one another out. So if this equation holds that the net force equals 0, then the same is true for both the x and the y components. So therefore, the sum of all the x components equals 0. Okay? And then the sum of all the y components is 0 as well. Okay? So let's start with the x components. What we need to do is find the x component of all 3 of these force vectors. The x components of all 3 of those have to add up to 0. So let's start with the right tension. Okay, the x component, this makes a 5-degree angle with the x-axis. So the x component is this little section here of this right triangle. Okay, and if that's a 5-degree angle here, the x component is given by the magnitude of the vector, TR, times the cosine of 5. So there's the x component of the right tension, TR cosine of 5. Now, what about the left tension? Well, it makes the same angle with the x-axis, but it makes it with a negative x-axis. So the length of the x component is TL cosine 5, just like this was TR cosine 5. This is TL cosine 5, but it's negative. Okay? So it's a negative force, TL cosine 5. Now what about the x component of this guy? What's the x component of something that points perfectly along the negative y-axis? Well, it's entirely along the y-axis, so it has 0 x component. So the x component of the weight is 0. So we don't even need to put that in there. So those are the x components of all those forces, and they have to add up to 0. So this equals 0. Okay? This is a pretty simple equation to solve. Divide both sides by cosine of 5. And add TL to both sides. And what you find is that the right tension equals the left tension. And that's not a big surprise. We'd expect the tension to be the same everywhere in that rope. And we're just going to call that T. And that's what we're trying to solve in this problem, is the tension of the rope. So we know that both this left tension and right tension are equal to T. Okay? So we can just go ahead and put that in right now. This is just T. Okay? It's no longer TL. And this is just T as well. Okay? So we just plugged our solution up into our diagram up there. Okay, now let's do the same thing for the y components of all these various vectors here. So the y components have to add up to 0. So we're considering the y components now. So what's the y component of this guy? Well, to figure out the y component, that's this little length right up here. Okay? And to find the side opposite the 5-degree angle in a right triangle like that, we have to use the sine now. So the y component of this vector, t, the right tension, which is now just t, is t times the sine of 5. Okay, so we use cosine for the x component. We're using sine for the y component. Now, what about this guy? The left tension now. Well, the y component of this guy is this as well. So it's still t sine of 5. So we get a second one here, t sine 5. Now, those are the first two vectors. What about our third vector? We need the y component of this guy. Well, its length is mg, and it's entirely along the y-axis, but it's in the negative y direction. So that's a negative mg. The y component of this is negative mg. And this all has to equal 0. So I'm running out of space over there. But that plus that minus that equals 0. Okay, let's do a little bit of algebra here. These add together to get 2 times the tension of sine 5. And of course, this is all equal to 0. We add, so remember, we're trying to solve for the tension. That's the question here. So let's add mg to both sides, divide by 2, divide by sine 5, and what you get is that the tension is mg over 2 sine of 5. Okay? Now what is mg here? Well, mg, that's the guy's weight, the tightrope walker's weight. And his mass is 70 kilograms. G is 9.8 meters per second squared. And that gives you the result 686 newtons, which is about 154 pounds or so. So that's what mg is. That's what the weight of the tightrope walker is. Now to find the tension we need to take this mg and divide it by 2, divide it by the sine of 5. And when you do that, you get a pretty enormous number. You get the number, I got 3940 newtons, which is 880 pounds. So there's our answer. There's the tension on the rope. So that might be a somewhat surprising answer. We have a tension in the tightrope that is about 5 to 6 times greater than the weight of the tightrope walker himself. And that's just the basic physics of that situation. If you have a really tight tightrope like that, the amount of tension generated when someone stands on it is enormous. So you better have pretty good anchors that are holding that rope in place, because they're going to have to hold 880 pounds of force. Not only that, but the rope better be pretty strong. It better be able to withstand that much tension. So forces really can multiply quickly in that type of situation where you have very sharp angles. In this case, we had a 5-degree angle from horizontal. Okay.